Let's look at another example where we have a single constraint. If weight b is moving downward with a velocity of 4 meters per second, which is decreasing at a rate of 1 meters per second squared, find the speed and acceleration of weight a. Now let's go over to b and let's point out what we know. We know that b is moving downward at a velocity of 4 meters per second. And we know that this velocity is decreasing at a rate of 1 meters per second squared. So we could say that we have an acceleration which is decreasing, so we want to use a negative value of 1 meters per second squared. Now we're looking for the speed and acceleration of weight a. Now we start off by going through those steps that we talked about. So we say, how many constraints do we have? Well, we've already seen this example, so we have one constraint here that connects a to b. Remember, these other cables don't really matter because they don't have an effect on a and b. So we have one constraint. We're going to use one constraint equation. Now we need to determine a datum line. And remember, a datum has to be from a fixed position. So again, this point, this line I should say, up here would work because it's fixed. This position here would also work because it's fixed, because again that pulley is constrained so that it can't move. So this would be a good choice for a datum. The next thing we have to do is we have to determine the position variables for the particles we're interested in. So for particle B, I could determine some kind of position variable. Let's say I'll use S sub b. Now remember, it's important to note that the position variable does have a positive direction. The positive direction goes from the datum to b, which means that movement in the positive direction will give you positive velocities. Now let's also look at a. Now we could take the position variable from the datum the whole way down to a line showing a, but we could also make a note and make it a little bit simpler for ourselves that this pulley is going to be moving at exactly the same rate that a is. So if we define where this pulley is, we'll be defining effectively where a is for the intents and purposes that we're interested in. So remember, the position goes from the datum to the particle. All right, the next thing we do is we write a constraint equation. So the constraint is the length of the cable. So we say L equals, now we have to determine all the pieces that make up L. So you can see from here to here we have a constant value. From here down to here we have S sub a. From here around to here we have a constant value which is half the circumference of that pulley. Then we have another value here which is S sub a. Another constant half semi-circumference, and another value here which is S sub b. So effectively what we get is 2 times S sub a plus S sub b plus several constants, which we're going to group together. Okay, we have a constraint equation. Now the next step is that we take the derivative of the constraint equation. So we take ddt of this entire equation. Again, if we take the derivative of L, L is not changing. We're assuming that this is an inextensible rope. So the derivative of L is 0. The derivative of 2S sub a is going to be 2 times V sub a. The derivative of S sub b is going to be V sub b. And the derivative of all those constants that we group together is going to be 0, which is why we grouped them together. So now we have a relationship that tells us how the velocity of A varies with the velocity of B. So we have a velocity equation. Now we also want to know acceleration relationships. So we need to take the derivative one more time. And when we take the derivative, the result is 0 equals 2 times the acceleration of a plus the acceleration of b. Okay, this gives us our acceleration equation. All right, now what we want to do is we want to look at the question and see what it's asking. It says it's giving us a known velocity and a known acceleration for b, and it's asking what is the speed and acceleration of weight a. So really this is a matter of using these equations and plugging in values. So let's look at the velocities. All right, the velocities. So we take our velocity equation. V sub a is going to be the unknown that we're looking for. And then we add V sub b. Now let's look at this value of V sub b. We have 4 meters per second. You notice it's going down. So the way we define the position variable for v, the position variable is defined going down. So that makes this a positive velocity. So we'll add to that 4. All right, now we can solve for V sub a. And we find that V sub a is -2 meters per second. Now the -2 meters per second, let's take a look up at the rest of the page again. If I have a -2, what that means is a is defined such that the movement down is positive. This is all having to do with the direction of the arrow that we put here. So if a is defined as positive down, and we got a velocity which is negative, then that means that the movement of a is going opposite the positive direction. In other words, it's going up. So we might want to specify an up arrow to be very specific that the negative means that it's going up. Now let's also take a look at the accelerations. All right, our acceleration equation says 0 equals 2 times the acceleration of a plus the acceleration of b. All right, now the acceleration of b is, again, it's decreasing going downward. It's -1 meters per second squared downward. Now let's take another look at our arrow to make sure we're very clear about this. If our s sub b is defined as downward and the acceleration is decreasing downward, then that means we're going to have a negative value, just as we discussed. So that gives me a -1 meters per second squared. Now if I solve for the acceleration of a, I find that it equals 0.5 meters per second squared. And I'm getting a positive value for 0.5. And remember, again, let's take a look at that arrow. S sub a is defined as positive downward. So if my acceleration is positive, that means that it's accelerating down.